Within a couple of weeks, the James Webb Space Telescope will be sending the first images back to NASA, and what images they will be, with the Webb probing the furthest reaches of the universe, peering further back in the time than ever before. Coming up next.
Podcasts you love.
From people you trust. This is TWiT.
This is This Week in Space, episode number 18, recorded July 1st, 2022. James Webb Space Telescope First Light. Hello and welcome to a very special edition of This Week in Space, the Webb Telescope First Light edition. I'm Rod Pyle, editor-in-chief of Astro Magazine, and I'm joined by my guest co-host, Sir Geoffrey Notkin of Meteorite Men fame. Say hello, Jeff.
Good afternoon. Greetings, Rod. Lovely to see you again.
Good to see you. And we are joined by Mark Clampin, who's generously made time for us out of his very busy schedule. Mark's the Director of Science and Exploration Directorate at NASA headquarters, was previously the project scientist for the Webb Space Telescope at the Goddard Space Flight Center. And lest I forget, he was also the director of NASA's Astrophysics Science Division, worked with the Hubble Space Telescope and the TESS Exoplanet Space Telescope before coming to the Webb. Whew. Hi, Mark. Thanks for joining us.
Hi. It's a pleasure to be here.
So I don't know about you, Jeff, but I feel seriously outclassed today. But as Mom used to say, each according to his gifts. So I'm going to try and get past it.
I know, same, actually. I'd been very interested in this project, but did a lot of reading and research beforehand in the hope that I might be able to somewhat keep up with Mark and ask some useful questions.
Exactly.
But you're brilliant with this, Rod. Between the two of us, I think we can manage it. I have faith.
We'll flubber through. All right. But before we start, it may come as a surprise to everyone that I have telescope jokes. All right. Hey, my telescope broke the other day and I was hoping the local observatory could repair it. They said they'd look into it. Okay. Yeah.
I think
Thanks,
that's really
man.
good, actually.
Right
I like that.
Oh,
that's
but
better than
still,
usual.
Well, that's not a very high bar.
Come on.
I think my neighbor is stalking me. I saw them Googling my name through my telescope. Okay. I had to wait for the crickets. Okay, let's do a couple of headlines, and then we'll get into the meat of this. We have a new double crater on the moon. This comes to us from Forbes magazine. NASA's Lunar Reconnaissance Orbiter, the LRO, has found the impact site of a recent rocket stage crash on the moon back on March 4th that we discussed on this podcast. We're still not sure whose rocket that was. It was an upper stage. First, we thought it was SpaceX, but they said no. It's now thought to be a Chinese spent rocket stage in the 2014 launch of Chang'e 5. We're still not sure. Interestingly, we've got two overlapping craters, one about 59 feet across, and the other about 52 feet. So it looks like a doublet, which is unusual because they only expected one depression from the impact, if at all, from the mass of the rocket engines, which is the heaviest part of a stage. So it speculated this was somehow heavy on both ends, whether that was unspent fuel in an upper tank or what, we just don't know. But what is cool is it's the first unintentional crash of a piece of man-made space debris. So
I have a question.
We go. Yes.
So, Rod, do the pieces of debris count as meteorites?
No.
Or no? Are you sure?
People don't make meteorites.
Well, but still, we've got a metallic object crashing on the moon, forming a crater and debris around the crater. I know it's human-made, but it's kind of cool to think about human-made meteorites on the moon.
Well, you're a special interest.
Actually,
so I'll give you that.
That sounds like a sci-fi film title: "Human-made meteorites on the moon."
It
Coming
does.
this fall.
Next up, Capstone. This comes from space.com. We have a new lunar orbiter, a CubeSat, headed out to the moon. It launched on June 28th on a Rocket Labs booster, which is a smaller launch company out of New Zealand. It's probably the least expensive launch of a interplanetary probe to date, if you can consider a trip to the moon interplanetary. And what's interesting about this, among other things, is it will enter the same orbit that the Lunar Gateway is going to use, which is our upcoming crewed space station that's going to be orbiting around the moon. It's called a near rectilinear halo orbit, which is a long oval orbit over the lunar poles, which has a number of advantages, not the least of which is it can be in continuous contact with Earth because it doesn't pass behind the moon for having blackouts. Capstone will take a long, low-energy ballistic trajectory to the moon, which is the same one that we plan to use for cargo missions to resupply the Gateway and Artemis. So this is a critical test of a number of things to keep the Artemis program moving forward on schedule. And we think that probe will be good for about 15 years. It will also be testing communications and guidance with the other lunar orbiters. So it's kind of a triple hit all around. So good luck, Capstone. And we will be back in just a couple of moments with our featured interview with Mark Clampin. Stand by. All right, we're back. And Mark, it's so good of you to join us today. I know you've been a very busy man. And can you give us a little more detail on what your role with the Webb Space Telescope has been over the years?
Yes. So my role has actually varied. In my previous incarnation, when I worked at the Space Telescope Science Institute, I was involved in some of the very early thinking about what some of the findings that were coming from the Hubble Space Telescope meant and how we could subsequently follow them up. But really, when I joined NASA in 2003, I joined to take up the role of observatory project scientist for the James Webb Space Telescope before it was even called that. And that role I was in for about 13, 14 years. And the basic, I always used to tell people, they say, well, what's the role of a project scientist? And I always tell them we're kind of the science police. So, the project scientist role on a mission that's being, formulated or designed, put together, and then assembled and integrated is to work with the engineers to make sure that the science requirements are met. And then during the integration and test phase, you're actually looking at real data to make sure the science requirements are met. And any time that the engineering team run into a technical problem, they're going to come to you and say, we're having problems meeting this particular requirement. Can you help us? And the project scientist's job is to work with the engineering team to make sure that we continue to meet the science requirements, but maybe look for ways that you can provide relief on a particular requirement so the project can move forward.
I love science police. That's a great phrase, science police.
Science cops, yeah.
Yeah, it always used to go down well when I did presentations. I should just add that, my current role, I'm the Director of Sciences and Exploration at Goddard. So now I manage all 4 of our big science divisions, which includes astrophysics, which is the division that is leading the James Webb Space Telescope. So I kind of have oversight pretty much of all the Goddard science missions on a science level.
All I can say is, wow. Before I get to the big question, can you just let us know, so the commissioning of the telescope in terms of all the mechanical functions that had to happen on the way to the moon went just stunningly well. So we've been watching the instrument commissioning. As I understand it, you have 2 instruments up and operating and chilled down now, the near-infrared imager and the slitless spectrograph instrument. What should we be expecting in the coming weeks?
So I think the way to look at this is, Webb has 4 main instruments and all of them are operating, but each of these instruments has different modes because Webb is designed to be an observatory facility. And what that means is it's designed to address a broad range of different questions in astrophysics. And to do that, you need a broad range of different capabilities. So all of the instruments offer different modes or ways of being operated. While we have all 4 instruments up and operating, we're going through calibrating each of these individual modes of the instruments so that they are ready to do science. And what that means in reality is that we know, for instance, how to put a target into an aperture for a spectrograph, or we know how to put a target under a spot for one of the coronagraphs. And then when the data comes out the back of these instruments and is downloaded, we send it back to Earth and process it. When it goes through the data calibration pipelines, we can then deliver data that's calibrated to the scientists who are going to use it, and it's ready to go to do science with. So that's why, people ask us, why is it taking so long to calibrate? Well, because we want to check that each instrument is behaving the same in space as it did on the ground before we launched it. And then, when there are updates or changes, we can make the adjustments in the data pipelines so that they are properly calibrating each of the instruments. So as you said, we've pretty much completed all the modes on 2 of the instruments, and we're just finishing up on the remaining modes for the remaining instruments. But, we're very close to finishing now, and, we're right at the point where we can start doing not just the early release observations, which have been taken and are being taken, but we can start doing these, what we call cycle 1 observations, or the first year of science observations.
And Mark,
really
is that, sorry, Rod, go ahead.
Go ahead. No, you please.
Is that, I read today that July 12 is the scheduled date for the first release of images. Is that still on the schedule? Is that looking
absolutely
accurate?
Yes.
Wonderful.
In fact, I spent most of my day talking about it to various people. So yes, it's going to be a big event. We're really looking forward to it. Most of us have not yet seen any of the images, so it's going to be really interesting seeing what these first science images from the observatory look like and how they demonstrate the performance of the telescope.
Well, I'm sure we're all holding our breaths. Sorry,
yeah.
to interrupt. Go ahead.
Exactly.
No, not at all. And just, one little more bit about commissioning. I think it's something that sort of gets underplayed in the press a bit. And I'm sure other people have said this, but I was talking to Mike Hecht at JPL a couple of years ago, who was the PI for the MOXIE experiment on Perseverance. And he made a comment that I love, which was, all instrumentation tests are doomed to succeed on the ground. So, you have to test these things in one gravity unless they've been up on the space station or on a flight. So I imagine more so for the mechanical deployment of the telescope, but even for instruments on it, there's probably a little bit of sweat when you're waiting for it to operate properly in a microgravity environment, right?
Absolutely. And, space is a very harsh environment. And, there are always slight changes in how the instruments perform when you get them on orbit as compared to in, special calibration chambers when you test them on the ground. There's the question of how they operate when you get them to temperature, and then, what changes do you see in the sensors when you start operating them in space, when they're, in a very enclosed system as opposed to on the ground where you're always running them with what we call ground support equipment. So there's always very small changes. But yes, we kind of tend to hold our breath every time that we, commission a new mode. And I'm, happy to say we've been very happy and indeed surprised by the performance. And of course, you alluded to the deployments, but this telescope has been very different in terms of how we've had to commission it. So we kind of had 3 phases. The first phase was all of those deployments. And as you know, the telescope is kind of folded up for launch. And then after launch, you have to go through a series of deployments. So that was, a very new thing for science missions, the level of deployment that we did for this mission. And, of course, we went through it in a very slow, methodical way. But, it was a very tense time and everybody was holding their breath at different places along the way. Once we got that done and everybody kind of breathed out, took a deep sigh, then we roll into the next step, which is that this telescope is not, what we call a field aperture mirror. It's 18 individual segments. And each one of those segments has 6 degrees of freedom plus a focus adjustment, and they then need to be all properly aligned so it behaves like a single mirror. So that was kind of the second phase, and having got the mirror aligned, then we could roll into actually commissioning all of the modes of the instrument.
Well, and as the press has loved to talk about in terms of mirror alignments, we're talking about widths of a human hair in terms of alignment accuracy, correct?
Actually, a lot less. I mean, just
good grief.
We're talking about hundreds of nanometers. So the wavefront error, or the error in the wavefront at the focal plane of the primary camera, is 150 nanometers. That's the specification. So it really is a very complex and challenging problem. And we actually did it in 2 phases. The first one is just adjusting what we call the mirror piston errors, so that each of the mirrors, don't have big offsets between them. And then we use a phase reconstruction technique, which is kind of interesting because it links back to Hubble. We actually use a technique that really was developed for understanding the spherical aberration on Hubble. And it basically involves taking images before and after the focus, and then using an algorithm to reconstruct the wavefront error and determine what adjustments you need to make to the mirrors to get them to the right place.
Well, Jeff, I have an analogy I want to toss you, and then I want you to ask your question.
Yeah, please.
So this is one of my favorite. The press, the media loves analogies. One of the best, and I think this actually came from NASA, was if the multi-segmented mirror was the size of the United States of America, the continental U.S., no error it would be larger, no surface error would be larger than a grapefruit, which just tears my mind into little pieces that anybody can achieve that.
I was going to read that exact same quote from the Ad Astra interview just now. It's so good. We think about precision and how carefully things are made, but that puts it into a perspective that it's hard to grasp that level of detail and accuracy. What I really
really
wanted
does.
Yeah. Go ahead. Sorry, please.
I was just going to say, it really does. And the other thing to remember is that this telescope mirror is, operating at around 40 to 50 degrees above absolute zero. So
which is very cold.
Which is extremely cold. Yeah, it's about around the ballpark of minus 400 degrees Fahrenheit. So that's an additional complication, and was a big complication when we were making and testing the mirrors, obviously.
Mm.
There's something that intrigues me on a slightly more personal level about the launch and the various stages the mission's gone through. So for many years, I've been friends with Dante Lauretta, the PI for the OSIRIS-REx mission, and I produced a documentary short film about OSIRIS-REx and went to visit it when it was being constructed in Denver, and we had an event in Tucson for the launch. And actually, the Drake building, the OSIRIS-REx headquarters for many years, was my immediate neighbor in Tucson. So we used to go over often and just watch Dante and his team communicating. But I observed his level of care and involvement with this mission, and I often thought it must be a terrifying moment when the launch actually takes place, when you've invested all of this time and effort into this. What were your personal feelings like at these moments of the launch moment and the deployment, when there's such critical sections of this mission that's been such a big part of your life?
So, it's an interesting question. I often get asked that, and I was actually, just to segue for a moment, I know Dante very well, and I was actually out there in Colorado when they did the final OSIRIS-REx tag and go from the asteroid. So that was obviously an exciting moment too. But for James Webb Space Telescope, we in this business, we tend to see a lot of launches, and as the director of 4 science divisions that are all launching missions, I don't want to sound blasé and say that the launch was spectacular, but for me personally, the thing that just made that morning was the final moment when it separated from the launch vehicle, and then we saw that solar array deploy. That was just astonishing, and everybody in the room I was in, and admittedly there weren't that many people, it was a few tens because of the pandemic, you could just hear this sudden moment of silence, and everybody's just staring at it going, wow, we weren't expecting that. And the reason actually turns out to be that, the Ariane launcher put it into such a perfect position that, that next piece, which was the deployment of the solar array, could start immediately. And so everybody was absolutely stunned to see that happen, and obviously very happy as well, because it meant that we could almost immediately see power on the spacecraft and knew we were good to go for that first part. As we went through the subsequent, 3 or 4 weeks of deployments, that was obviously more of a sort of slow motion thing. It's like watching grass grow. I think, soldiers always say that combat's, the long periods of boredom, interspersed with moments of terror. And that's kind of what it was like. It would take a very long time to do things. And then you get to that moment where it finished and completed and you knew you got there, and everyone's kind of sitting there, staring at the monitors, waiting for that last bit of telemetry. It says we're there and we can move on to the next deployment. So it was very tense at moments, but it was, in retrospect, astonishing just how smoothly it went and how everything did what it was supposed to do in the way it was supposed to do it. And I think that's a testament to the quality of the integration and test program that we ran on the ground to make sure this whole sequence of deployments would work.
Well, congratulations. Marvelous answer.
So here's the big one, and we don't have a drum roll loaded up, so I'll do one myself. I'm not going to ask you what the first images are going to be, because I know everybody is, and that's not fair, right? But can you talk a little bit about what your first research priorities are going to be and what kind of things we might expect you to be looking at in the next 6 months?
Oh, absolutely. So I actually think that Webb has taken, a very interesting approach to how it does science in the first year. So as you know, the original idea is it was conceived by the team led by Dr. John Mather, was that, Webb was designed to find the very first galaxies or, objects, in the universe. And, to find them, we need to look back to about, 1 to 300 million years after the Big Bang. And the reason that we built Webb is because those objects are basically too red or in the infrared bandpass to be seen by Hubble. So that's obviously going to be a big focus of the first year. People will be doing these very deep field images, much the same way that we've done them with Hubble, doing them in 4 or 5 different colors probably, and then putting them together, looking for the reddest objects. And there'll be the follow-up using spectroscopy to see whether or not you can say, yes, these are some of the very first objects that formed in the universe. But Webb is an observatory, so there are going to be lots of different programs. A big focus will be the formation and evolution of stars, looking into these dark clouds. Hubble takes these beautiful pictures of these big clouds of dust in the sky, but you're really just looking at the outline of a big 3D structure, and you can't see into it. You just see these beautiful sort of structures. James Webb, with its infrared vision, can actually see inside these and will allow us to study the chemical composition of these clouds and also actually image and look at the range of different objects inside these clouds at different stages of star formation and evolution. For instance, to answer questions like, when do planetary systems form? What are the conditions for those to form, and so on. And then the last really big theme is the search for life. And I actually find it interesting that over the lifetime of the mission, as we've been formulating and then building and testing this observatory, this whole new technique of studying exoplanets has become, very popular. That technique is called transiting spectroscopy. And basically, you take spectra of a star when the planet crosses the face of the star, and you see a very small dip in the light. And you can, if you are taking spectra, actually back out the spectrum of the exoplanet, if you have the right level of contrast. So when I joined the program in 2003, this technique had literally been used on a couple of objects. And now, it's being used by Hubble to study gas giant planets. But it's a very difficult technique. You need to collect enormous amounts of light to get the signal levels required to get the atmospheric composition of the planets. And with Webb, we'll be able to sort of move down into studying what are called sub-Neptune-sized planets, and then down to hopefully super-Earth and Earth-like planets as well. So that's going to be a really big focus of this telescope. And if you look at the breakdown of observing time that's been peer-reviewed and then awarded based on merit for the first year, there's a lot of time being spent looking at exoplanets, because this is, I think, really one of the killer applications for Webb.
I'm so glad you mentioned this, because this is something that really fascinates me. And I know this is an area in which you have particular interest, Mark. So do I understand correctly that by studying spectroscopy of the atmosphere of exoplanets, it may be possible to detect biological markers if there was biological activity on said planet?
That's exactly correct, and there's a whole sort of group of the exoplanet community who work on, talking and modeling what are called biosignatures. And so we will be trying to look for some of those in these systems that we're going to study. Now, I think it's always important to point out that most of the systems that Webb is going to study are not like our own solar system. So, we live on a small rocky planet that takes a year to go around its sun, and its sun is a big solar type star, G star. Most of the systems that we're studying with Webb, we'll be able to study because they are planetary systems where the planets orbit the star on a timescale of days to months. And those stars are very low mass M stars. And it's the fact that the planets are relatively big compared to the star that you can do these measurements. And of course, the fact that, they eclipse very often because the year around these stars is, a matter of days to months. So they're very different systems. And of course, I always think it's a little arrogant of the science community to sort of think of the potential for life in terms of looking for exact analogs of, our own, solar system. So this is obviously an important, problem to address, and, understand whether these systems really could, harbor life, and do they, could we find biosignatures?
Well, and you've touched on another thing that absolutely fascinates me, Mark, which is, yes, we do seem, understandably, because of biological research done on Earth, stuck on this idea, well, we would have to look for signs of life in similar systems or under similar circumstances to our own. But is that really the case? Is it possible that there would be life that's so different from what we have encountered on our own planet that it could exist in a different type of system and would be a surprise? What are your thoughts on that?
I completely agree. I think it's foolish of us on basis of very small number of statistics, i.e. our own system, to make that assumption. And, one really needs to go and collect data and do observations. And of course, even in our own solar system, we're talking about looking at some of the moons of Saturn and Jupiter as being potential locations where life might exist as well. So I think you have to keep a very open mind as a scientist and just make the observations and see where the science takes you.
Wonderful. Very well said. Well, there are going to be a lot of observations coming soon, aren't there? Lots of many years of data for you to analyze in the future, I imagine.
Absolutely. And, one of the things I sort of mentioned and then I didn't quite get to it. So we have a program called Early Release Science with Webb. And the idea was that, and I sort of touched on this at the beginning, these instruments are very complex. They have lots of different modes. And until you actually start doing science with them, you never know which mode is the best for doing a particular problem. I mean, obviously, if you want to take images, you need an imager. But when you start doing things like spectroscopy of exoplanets or getting spectra of galaxies, there are different options that you have on the telescope, and different modes will give you different resolutions, and there's a lot of parameter space to understand to figure out what is the optimum mode for a particular observation. So the early release program is something like 13 programs that span a wide range of different astrophysical problems. And basically what NASA has done is said, okay, science community, go form these big groups, give us some examples of how you would use the instruments and explore the capabilities of those instruments. So in parallel to the time that's been awarded competitively, these 13 programs, which were also, I should say, awarded competitively, will be run, and it will allow people to see very quickly, because the data will be immediately public, what kind of opportunities or what kind of capabilities they could apply to their own science problem in the coming years as we compete for new science programs every year. So we're trying to kickstart the community and give them a real good run at getting great science programs in over the next few years.
So I'm starting to get chills listening to what to expect. And just in terms of the life science part, my interest in this goes back to seeing Viking landing as a young man, which was a spectacular mission. But when you look at the kind of life science experiments they did, they're almost charmingly naive. We'll pick up some sand, we'll inject some nutrients in it and see what happens. And the distance that NASA's come since then has been spectacular. We got to take a break, but when we come back, I'd like to talk about the whys and wherefores of infrared astronomy a little bit. And we will be back after this short message. And we're back. So the Webb is an infrared telescope, which introduced in itself a whole host of complications in terms of how far it had to be from Earth, how it had to be oriented. You have to be able to chill it down to these extreme temperatures, as you've already mentioned. And I think something that a lot of people wonder about is why infrared? And in particular, for myself, I know that part of it is because infrared wavelengths travel through the intergalactic dust better, but I've always wondered why that is. Is it because the dust is absorbing a visual light, but visual spectrum light, but not infrared?
Yeah, I mean, it's all basically to do with the size of the dust particles in these clouds. But I think the real reason the Webb is an infrared telescope is really the first galaxy problem. And that is that if you look at what Hubble has been able to do, the Hubble deep fields take us out to about 1 billion years after the Big Bang. And the way that you study those galaxies is to do what's called the dropout. So you look for images of different colors in the visible with Hubble. And then when you see the galaxy disappear, that allows you to make an estimate of the redshift of the object. So for instance, if you take an image at 400 nanometers, 600, and then 800, when you stop seeing the image, when you see galaxies where you can't see them at 400, but you can see them at 6 and 8, that gives you some idea of the kind of redshift of that galaxy. And then when you can only see galaxies at 800 nanometers, that also gives you different information and tells you that's more distant. The problem we have with Hubble is that it's a warm telescope. So when you get to about 1.6 microns, you can't go any further. So if you really want to look at those galaxies that are of redshifts of, greater than 10, 10 to 12, you really need to have an infrared telescope that can image at those wavelengths. And that basically means then that you need a cold telescope that isn't going to, first of all, image its own thermal signature. So that's the real reason that, Webb is an infrared telescope. It was that deep imaging problem.
And this is kind of a simplistic way of putting it, but in a sense, more than anything you've flown before, the Webb is kind of a time machine. How far back towards the Big Bang are we looking? How far after the Big Bang is the first light we're going to see from this?
Well, we really want, most of the theoreticians tell us that the first galaxies probably appeared about 100 to 300 million years after the Big Bang. So that's where we're looking. If you look at what Hubble's looking back to about 1 billion years after. And there are a few examples where we've been able to find objects in what are called gravitational lens enhanced images that allow us to see back a bit further, but they're very unique objects that are sort of specific to that particular cluster of galaxies that are lensing the background objects. So it's a whole new parameter space we're opening up here.
Yes,
we've mentioned Hubble. We've mentioned Hubble a few times, and I'm really interested in some numbers and statistics here, Mark, if I may. So if I remember correctly, Hubble is orbiting Earth at about 600 kilometers distance, and yet the Webb telescope is millions of kilometers away. It's been sent to the Earth-Sun L2 Lagrange point, which is just in itself an enormous technical achievement. So perhaps listeners who are not completely familiar with this project in the space news, this concept to me that the telescope has gone so far that it's what would we say, approximately 4 times the distance of the moon's orbit from Earth. Yeah. So it's far out in space, away from us, and is this in part, if I understand correctly, so the telescope is shielded from a large amount of the sun's light pollution by being positioned with the Earth positioned between the James Webb and the sun. Am I understanding the science correctly here? Yes,
and a colleague of mine, Chuck Bowers, once reminded me that if you're in low Earth orbit, the Earth is a very big object underneath you. This came from a discussion of stray light and why our models were seeing some stray light for a completely different program. But that is true. And if you look at Hubble, of course, it's got a big tube which protects the telescope from a lot of stray light. But the downside of being in low Earth orbit is, in Hubble's case, goes around the Earth every 90 minutes. And half of that time it's in daylight. And the other half it's in nighttime. And it's continually heating and cooling very slightly because, when it's in daylight, it's being illuminated by the sun. And then when it goes into nighttime, it cools down. And then you've got these two places, where it transitions, where it's actually changing very rapidly. So if you want to build an infrared telescope, low Earth orbit's not the best place because you've got this sort of continually changing thermal environment. If you go out to L2, it's a lot more benign and it's just not changing. And so the telescope can sort of settle down to its operating temperatures and it isn't changing drastically every 45 minutes. So that's the primary reason we send it out there. The other big reason, of course, is that, Hubble loses half an orbit every orbit due to the fact it can't do science on the day side of the Earth. So at L2, you're actually able to just do 24/7 science. So you're much more efficient as well. And I probably should also just mention that we actually aren't at L2. We orbit L2 in a very big halo orbit because you don't want the telescope being in the shadow of the Earth.
Well, and because we have Mr. Meteorite with us, I have to ask, I know that L2 is a place that also attracts other objects that can hang out in that orbit. So you've had a couple of small micrometeorite impacts. Did I get that right, Jeff? Yes. Micrometeoroids in space, correct?
Oh, very well done.
Oh, thank you. How much of a concern is this? I know you've had at least one, but I assume that this was factored in from the beginning and that the instrument's very tolerant of smaller impacts anyway.
Exactly. So NASA actually at the Marshall Space Flight Center maintains a very detailed model of the micrometeoroid environment at L2 as well as a number of other places. So we kind of knew what environment we were launching to. And one of the things that we did for Webb is, design the performance to what we call the end of life requirements rather than the beginning. So as you said, it's always been factored in that we would get, a certain number of micrometeoroid hits based on the model that Marshall provides to us explaining, predicting, how many hits we're going to see. So we did a lot of testing on the ground to make sure that, the flux that we would see was not going to have a major impact. It has a very marginal impact on the mirror quality over time, but it was expected, and we're working with it.
You mentioned coronagraphs earlier, and I was thrilled when I saw long ago that there were going to be a coronagraph, was going to be a coronagraph on this instrument. Can you talk about those a little bit, what they are and how you'll use them and what you might expect to see?
Right. So coronagraphs are instruments that allow us to see very faint material around very bright objects. And, the simplest analogy that I have always come to is, if you're driving at night and somebody comes towards you with their lights on beam, you kind of do this just to cut out the light. And that, blocks a lot of the light so you can see enough to, continue to stay on the road. What we do with a coronagraph is we essentially move the telescope so that the star we're studying goes behind a dark mask. And then we do some work with the optics to, suppress what we call the diffraction pattern from the optics and enhance the contrast around the star or whatever object we're looking at. So it's designed to allow you to look for things like dust disks or, brighter exoplanets that are orbiting at a large enough distance that you might be able to see them. So we actually have two instruments with coronagraphs. The NIRCam, which is the near-infrared camera, has several different coronographic masks, different sizes. And then we also have a coronagraph in the mid-infrared instrument as well. And we're going to be using those to study, basically to look for very young exoplanets in the sort of 10 to 100 million year age regime, where they're still sort of slightly warm as they cool down, and basically look for planets in that, at that point in their evolution.
This is sort of a general question, maybe a little on the vague side, but Mark, what would you love to see when you're using the coronagraph? You're discovering exoplanets. You're studying them. What would be a really exciting discovery? What would make the team's day if you said, "Oh, we've just discovered"? Fill in the blank.
Yeah, absolutely. So I'll give you two examples, and one of them does come back to the coronagraph. So I was actually on a team several years ago that observed a star in the southern hemisphere called Fomalhaut. And Fomalhaut has a big debris disk, or belt as we call it. And my colleagues and I actually discovered what we think is a planet, but we're not entirely sure at this point because it's become somewhat controversial detection. So I'm really looking forward to seeing what Webb finds when it studies Fomalhaut. So it was always kind of a very tough detection. Some recent papers have claimed that we didn't see a planet. We just saw a collision between two large objects at the edge of the belt, and that's produced a dust cloud. So we can clear that up using the Webb telescope because it will get a very, nice infrared image of what's going on there. And if it's a planet, we'll be able to see a point source. If it's a cloud, we'll be able to tell from the size of the remaining debris, if indeed, it hasn't completely dispersed.
Sorry, go ahead.
Sorry.
Please. No. You've got your own passion project attached to this. You must be really looking forward to the day when you're able to examine that.
Absolutely. And, it's been sort of interesting over the last, 5 or 6 years watching all these papers come out speculating on what this object might be, whether it's there. So it's time to sort of make a final assessment of what's going on in Fomalhaut. But I'll also say, the other sort of passion project is I'm part of a team that's going to be looking at a very famous exoplanet system called TRAPPIST-1, which is seven planets. They orbit a very low mass, very cool star called TRAPPIST-1. And about 3 of them are in that region of the orbit around this star where there may be liquid water on the planets. So we're going to be looking at the atmosphere of one of these objects in great detail using the transit spectroscopy technique to see what we can see.
How exciting.
So
Yep.
I would imagine that between you and your staff, you have a lot of proposals for people that want to take observing time on this instrument and different projects. How does one sift through that and determine what's going to go when?
So for the Webb Space Telescope, it's managed in the same way that we manage the Hubble Space Telescope. So each year there is a call for proposals, and the Space Telescope Science Institute in Baltimore puts together a series of peer review panels, and they each review proposals for a particular area of astrophysics, and they basically grade them based on the merit of as perceived by the peer review group, and the best proposals are the ones that get time. Okay. And we've done a few things over the last few years which I think are a great leap forward. A concept called dual anonymous. So the proposals are written in a way that you don't get to see names or on the proposals. So it kind of takes out some of the bias when they're reviewed. Really, you're just now we're just reviewing the science, and there's not this tendency to say, well, this proposal's written by person X, and I know them, and it must be a good. It's really just the science. So we're also making, I think, a lot of strides in being more inclusive and making sure we really are picking the best science ideas. And you can see that in some of the proposals that were picked for the first cycle, where we have graduate students and postdocs winning time on Webb, which is just great.
This is good news, Jeff. You and I can send in our request.
Whoa, we better
won't
get
know.
Scribbling, Rod.
Yeah, we better be.
It's such a. I want something else. Please go ahead, Rod.
No, I just say I want to give you a couple more questions, and then I'm gonna hit them with my big wrap up. But I think
sure.
It's your turn.
Well, I think that leads to something that I found very intriguing. Mark, you're talking about a democratic process that allows proposals. So there are projects on board the James Webb which are the purview of University of Arizona, the Lockheed Martin team, European Space Agency, NASA JPL, Canadian Space Agency. That's a pretty fantastic international group you have there. How have you found the process of working with so many different groups in different countries? There must have been some diplomacy and good management involved in organizing all of that.
Absolutely, and I cannot say enough good things about all of the different teams that have worked on James Webb. I mean, they've really come together. Everybody has always been focused on just making sure we can do the science, making sure that we're building the best possible experiment we can. And, we've always been able to resolve, issues and differences. At a sort of more legalistic level, there are laws in the US about export of technology, and we've had to work around those. But one of the things that we did at the Goddard Space Flight Center very early on was have a sort of legal point of contact who worked very closely with the Goddard team and then with all of our international partners to make sure that we, weren't doing anything that was, problematic, and to make all of the, technology export requirements be met as simply as possible, bring people into the group so that they could work with the engineering teams. So all of that really came together. And again, it's the fact that everybody's focused on the mission, on doing the best possible science with this telescope. And that's really, led to, the success you see today.
It's marvelous. And I've got one more fun question, if I may. This is a very specific thing, but this is something that delighted me. So I'm always impressed when a very large scale project like this doesn't only look at the problems that need to be solved in order to fulfill the mission. But what might we need in the future? And so I loved this anecdote about the trailer hitch that has been built into the telescope with the thought that perhaps at some point in the future it might be moved, it might be towed, there might possibly be a refueling mission. I realize there's a lot in the now to be excited about, but I was very intrigued by that aspect of forward thinking. Well, maybe in the future, many years down the road, we'll still be able to upgrade it or move it. I love that. Any comments on that idea?
Yeah, and it's obviously very forward-thinking. The possibility that we would want to refuel this in the future is very real, and so the capability is there. People always ask us, well, why can't you service it like Hubble? And the main reason is because it's a telescope designed to work in the infrared. It's a cryogenic experiment, and every single piece of hardware inside that telescope, is covered in, insulation, in multi-layer, insulation wraps. So cryogenic telescopes are very hard to service, is the bottom line. And you can't just open a door and pull an instrument like you can with Hubble, where you've got instruments operating at room temperature because they're maintained by heaters. In order to get to those really cold temperatures on Webb, you have to do a lot of insulation that prevents you from being able to treat the instruments like pull out boxes. But yes, we have got the facility there to refuel it in the future should that become possible for L2.
Excellent, thank you.
So I think my big sort of wind up here, if I might, and I'm trying to ask this in an intelligent way so I don't sound like a dolt, but you're in a unique position to sort of look into the future here. And I know you don't have a crystal ball, but if we were come back together in 2 or 3 years and discuss sort of what was, the wonderful thing about good science is it generates more questions with every answer you get, right? But if you were going to look at what the story is, I'm not going to ask you what you think you're going to find unless you want to talk about that. But, what the big story will be for the public in 2 or 3 years out of this, what will change our lives and the way we view ourselves in the universe?
So I think that there are sort of 2 elements I would talk about. One is, I think, Webb is going to, and obviously I'm biased, but Webb is going to do absolutely amazing things studying exoplanets. And we're going to find lots of new things about planets that orbit other stars in our galaxy that will help us understand, our place in the universe, as it were. But, one of the things that always excites me is the stuff we don't know we're going to find. And, I always again point people back to Hubble. We built Hubble to solve 2 or 3 problems. And I talked to you today about the problems that we built Webb to address. But it's the stuff that we didn't know we were going to find, I think, that's going to prove, very exciting and interesting as we start doing science with Webb. And that's one of the great things about these observatories. They provide such a quantum leap in performance that, you're going to find really great stuff to address the problems that you built it to do. But then it's all the other stuff that kind of appears because you've got this new super facility that has this amazing performance.
Well, that's a great answer, and it's very exciting. Jeff, do you have anything else you want to ask?
I just want to thank Mark for a fantastic presentation. Yeah. It's been so informative, and I meant to comment that I was delighted to see that you were that one of your alma maters is the mighty University of London, and I grew up in Greater London, so that was nice to see.
Yeah, thank you.
Old home week. Well,
indeed,
Mark, I just want to thank you from the bottom of my heart for joining us. I know you've got a lot going on. I would love to have you back in a few months as time allows, and your schedule allows, if that's possible. And I expect to see smoke pouring out of TWiT servers in a matter of weeks, and people realize that we had this conversation with you right before we get those first results back. So thanks again. Where would you recommend people go to see the latest on the web and on your activities?
So a number of places. You can go to jwst.nasa.gov, and there's some great web pages. The actual 12th of July event is going to be publicized on NASA TV. So that's a great place to watch the unveiling of these images. And I'll just add, I'm happy to come back in a few months. I think, we're going to have a lot of really great stuff to talk about. And as I said, the early release program where people are sort of road testing some of those modes is all public and is all going to be available. So there's going to be lots of stuff coming out very quickly.
And I wanted to echo what... Sorry, Rod, go ahead.
I was just going to say, as a young man who struggled to survive in UCLA's astronomy department for a year and a half, my hat's off to you and your expertise, the expertise to your colleagues on this incredible program. Jeff, go ahead.
I just wanted to echo really what Rod said, Mark, that you must have so much going on in your life, a very exciting culmination of many years of work. And it's very gracious of you to make time to be a special guest on the show, so close to the unveiling. So I'm sure I speak for all astronomy and space enthusiasts when we say congratulations, and we look forward eagerly to these results. And it has been such a privilege speaking with you.
Well, thank you very much. And I just want to emphasize, this program has been a very massive team effort. And I just want to acknowledge all the contributions of everybody who's worked on it over the years.
Yeah, it was a big effort. I think that's an understatement. I remember seeing it down at when it was in Los Angeles in the high bay there, and thinking, watching them testing this massive instrument in a full 1G environment, and thinking, 400 plus moving parts and all the other stats we've heard. Just a remarkable accomplishment. So we look forward to much more. I want to thank everybody for joining us today. Thanks for listening. You can send us feedback at TWIS@twit.tv. That's TWIS@twit.tv. We always look forward to your emails. New episodes published every Friday on your favorite podcatcher, so make sure to subscribe and tell your friends. Give us a rating, as many stars as you can, because we live and die by your opinions. You can always head to our website at twit.tv/TWIS. You can follow the TWiT Tech Broadcast Network at TWiT on Twitter and on Facebook at twit.tv on Instagram. Thanks very much, and we'll see you next time.
Listeners of this program get an ad-free version if they're members of Club TWiT. $7 a month gives you ad-free versions of all of our shows, plus membership in the Club TWiT Discord, a great clubhouse for TWiT listeners. And finally, the TWiT Plus feed, with shows like Stacy's Book Club, The Untitled Linux Show, The Giz Fizz, and more. Go to twit.tv/clubtwit, and thanks for your support.